Welcome to Westpak's webinar on packaging dynamics. This is the fifth and final in this series. I'm Greg Swinghammer. I will be your moderator and webinar organizer today. Before we get started, let's take a moment to ensure that everyone is ready and familiar with the webinar control panel. First, you should have a control panel on the right side of your screen. You may minimize this panel by clicking on the orange arrow button in the upper left-hand corner. You may expand the panel by clicking on the same button. Secondly, you have the ability to submit questions using the chat pane located near the bottom of the control panel. We will be answering a few questions during the webinar. However, if we are unable to address all of the questions during the webinar, one of our presenters will follow up with you via email afterwards. Today's webinar and slide deck should be available on Westpak's website on Monday. With that, let's get started. Today's presenters are Herb Schoeneman and Edmund Tang. Herb is the founder and chairman of the board of Westpak and a lecturer at nearby San Jose State University. Edmund is a lab manager here and has been with Westpak for over 10 years. He also lectures at San Jose State. If you would like to listen to the first four in this series or any of our other webinars, please check Westpak's website at www.westpak.com under the Events tab. Herb, take it away.
Thanks, Greg, and welcome to the Packaging Dynamics webinar. This is the fifth in a series of 5 webinars on protective package design, testing, and evaluation. Edmund Tang and I will be your hosts in this tour, and we have a lot to cover, so hang on tight. Let's get moving. If you recall, back in January, we told you that we were going to ambitiously look at giving you all the equivalent of a college degree in packaging dynamics in a mere 5 sessions, and here's how we did that. So we started off with defining and the terms and giving an overview of the whole process. We looked at quantifying the distribution environment. That was in March. We determined the vibration and shock sensitivity of products and test results. We reviewed cushion dynamics and testing and some level of package design. And then now in September, we're going to give you the design and testing portion of this webinar series on protective packaging, and especially how we know when we've got the job done correctly. So briefly, we're going to review webinars 1 through 4, go into the steps involved in the package design process. We'll look at the testing of package systems that are commonly used, some of the protocols, touch briefly on stimulation versus simulation in that testing. We'll look at the diagnostics of the results that we get, and it's to give you a better idea of when you can tell if the job's done correctly or not. And then we'll talk about the supply chain aspects, in particular logistics and cube utilization. So webinars 1 and 2, we talked about the terminology. It's kind of the lingo of the trade, as I call it. And we relied heavily on a single degree of freedom spring mass system. I hope you remember that. We'll touch briefly on that again during this session. We talked about the hazards of the distribution environment. We talked about the 5-step procedure for protective package design and testing. And then we also delved deeply into environmental quantification. Edmund, can you tell us about webinar number 2?
So webinar number 2 was step 1 of the 5-step method, which is pretty much to define the environment. Now, to define the environment is really important because you want to know what your package, your unit, is going to see when you ship it out. And depending on its hazards, it could be really, really severe or not so severe. So take, for instance, you have a single parcel package versus a pallet. Single parcel package will obviously see more impacts than a pallet, and then so you have to design accordingly. The pallet itself will see its fair share of impacts, but it will definitely be less. But they'll just see different type of hazards. So when you define the environment, you're quantifying the severity of each test input or each input. And then when you quantify everything, you want to make sure that it's accurate, because if it's accurate, one thing that you definitely avoid is both over packaging and under packaging, and to define, and that's the only way to actually pretty much have an optimal package if you have an accurate representation of your distribution environment.
Webinars 3 and 4 are what I call the heart and soul of the packaging dynamics curriculum. By defining the fragility or sensitivity of a product to dynamic inputs, primarily shock and vibration, we're able to uniquely tailor the product and package to the intended environment in an optimum way. No more guessing about how much packaging is required, no more embarrassment about products damage and shipment, and no more embarrassment as well about wasteful overpackaging. Okay. In webinar number 5, this one, we're going to talk about package design. We'll review some of the design details that we covered in the last webinar, and then go into how this is an engineered product package system and how we actually test it to see how well we've done. We'll spend a considerable time talking about the data that we're looking for and how to determine, again, if we've done the job correctly. You will remember this bar chart from our last webinar series. This chart was the ingenious invention of Mr. Bill Kipp, formerly of Lansmont Corporation, and true genius of our trade. During our last webinar, we detailed the process necessary to quantify each of these bars. And in webinar number 3, we quantified the product fragility bar, as you see here. In webinar number 4, we concentrated on the package bar, if you will, and how we quantify that bar. And in particular, we looked at cushion material evaluation, how we test cushions for both our impact and vibration absorbing characteristics primarily. In this webinar, we're going to look at the last 3 bars where we put the product and package system together. In other words, we design the package and we test the package for its ability to meet the requirements of the distribution environment. What we're really trying to do is to make sure that the product package system just meets the inputs necessary or going to be experienced from distribution. In this particular case, it falls short, so that's why we have damage in shipment. In this particular case, we have a package system that's very much more than what we need for the distribution environment, so that's wasteful packaging. And in this particular case, we've actually ruggedized the product so that the package occupies less of our out-of-pocket expenses. So the first step in this whole process is to design the cushion system. And the first step in that is to determine the thickness of the cushion, or more correctly, the required deflection of the product in order to achieve the results that we're looking for. This is particularly important when designing the cushion system to protect against impacts during distribution, because they require the most deflection. Various types of cushion systems have different dynamic inputs. They respond differently. So some deflect a lot before they bottom out, some not very much at all, and most of them are in between. Even if we are using cushion systems other than polymeric foams, the same deflection calculations are required. Remember, the product really doesn't know or care what kind of cushion surrounds it. It only knows how much shock is transmitted to it. So, selecting the cushion thickness, first of all, requires determining the deflection necessary. And this comes from a very simple formula. You can see it here, delta x, which is the change in dimensions, is equal to 2 times the drop height, h, divided by quantity acceleration, or g level, minus 2. Okay. Very simple formula. We have an example of that might be calculated a little bit further on. But remember that this number, this delta x, gives the theoretical deflection necessary, not the overall cushion thickness. In general, cushion materials will compress a certain amount before they bottom. Polyethylene foam, for example, is a pretty good material, and most of you are aware of it. It'll compress somewhere between 50 and 60% of its total thickness before it starts bottoming out, in other words, getting harder. More flexible materials such as polyurethane foam will compress up to 75% before starting to bottom out. So different materials have different compressive values and what I call the efficiency. Okay, here's the design example. Suppose that we're trying to achieve a 50G response from a design drop height of 35 inches or 90 centimeters. So in this particular case, going through the formula, we see that our delta X, which is our deflection, winds up being about 3.75 centimeters. Okay, so this isn't the total thickness of the cushion. This is the deflection we need. So let's suppose we're going to be using expanded polystyrene. That's the EPS foam. Has an efficiency or optimum strain of about 40%. So this total thickness required is 3.75 centimeters deflection divided by 0.4, which winds up being about 9.4 centimeters, or about a little over 3.5 inches, and so on. If you're using a polyurethane foam, you see it's much more efficient. You're only going to need about 4.5 centimeters, or about 1 3/4 inches or so. So that's how you determine the thickness of the cushion. Step 3 is to again divide that required deflection by the cushion efficiency to obtain your total thickness. We just went through that example. And then the fourth step then is to determine the optimum loading. This is the weight per unit area on the cushion, so that you satisfy the cushion vibration requirements as well as the impact requirements for that particular thickness of material. So that's the process, and it's relatively straightforward. We're going to go through this in more detail and let you know exactly what's necessary here. You've seen the top curve before. This is a graphical representation of what I just explained. The top curve is a cushion curve. It shows a plot of static stress versus transmitted deceleration for a given thickness. There's two thicknesses shown there, as well as for the drop height that will result in a transmitted deceleration on the vertical axis below the product fragility. The lower plot is what we call an amplification attenuation plot, and this shows the vibration characteristics of the same material. So what we want to do is to find the loading that will satisfy both the impact and the vibration attenuation characteristics for the required product usage. Okay. Edmund has some pretty good graphical means of showing this here, so Edmund, take it away.
Thanks, Herb. So one thing I like to do as a student and as a teacher is just give examples, because, one thing that I learned is that you learn by doing. And then, so this example here, we talked about it last week, so it's kind of sort of like review. Not last week, last webinar, sorry. But we had a vibration resonant frequency of a laser that was at 70 hertz. And then we also determined that the critical acceleration was measured at 70 Gs. So if you have a product with these characteristics, and you have the cushion curves on the right, amplification attenuation curve as well, how would you go about designing a package system? Where do you load? Where can't you load? That's the question I want to ask here. So first thing we want to take care of is just the vibration. So if your resonant frequency is at 70 hertz, you just want to make sure that at 70 hertz, your package is attenuating at that frequency. So you could do that by easily just drawing a horizontal line at the 70 hertz mark and seeing where it intersects the attenuation zone. So you look at that, and it intersects the attenuation zone around, I would say, 0.8 psi. And you draw a line straight down vertically just because we're combining the amplification attenuation curve as well as the drop curve together here now. So next we have the impacts of the shocks. So kind of sort of like the same manner, at 70 Gs, again, we're going to draw another horizontal line. And what that tells you is that, okay, we want to load it within that range, which is around 0.66 psi to 1.33 psi. And that is using the 3-inch foam cushion. So if just looking at just a drop cushion curve, it clearly shows that the 2-inch foam is inadequate because no matter where you load it at, it's always going to see more than 70 Gs. And the 4-inch foam is just a little too wasteful because, well, it's one more inch than the 3-inch foam, and then also we have a wider range. But then if we just do our due diligence, we could actually go hit the 3-inch foam, and that's what we're going to do. So combining both the vibration and the shock curves and the values, we get a workable range of around 0.8 psi to 1.33 psi. So theoretically, if you load your cushion system at anywhere between there, you should be safe. Okay, let's delve more into this example right here. So in the previous slide, what we determined was that the combined range for both amplification attenuation curve and the cushion drop curves is that in order to satisfy both criterion, we want to be anywhere between 8.8 psi and 1.33 psi. So let's use this as a specific loading here. So for this example, we are loading it exactly at 1.0 psi. And what does that mean for us? And let's just make sure these values check out. So the first criteria of vibration we're going to look at right now, we're going to look at where the line intersects the attenuation zone. And if you look at that, it intersects at around 65 Hertz. So our first criteria is that for vibration, attenuation at or before 70 Hertz. So 65 Hertz is less than 70 Hertz, so we know that that is good and that is satisfied. Second criteria is the drop criteria. So with the drop criteria, we have the goal of having each deceleration level less than 70 Gs. So in the same manner, at the 3-inch curve, we want to look at how many Gs is going to be transmitted at 1 psi. And if you look at that, it is around 65 Gs. And again, you do the comparison, 65 is less than 70 Gs. So we know that we're good with the drop criteria as well. So theoretically, loading at 1.0 psi would give us a satisfactory package system. We're going to talk about what happens if we run into some problems here.
Thanks, Edmund. When the loading necessary for proper shock and vibration requirements don't coincide, and that is somewhat often the case, then we recommend the use of ribs on the exterior of the cushion. And so I'm going to give you some parameters on how that can help make the job a little bit easier. And those parameters consist of, in the first case, that the loading at the peak of the rib is for vibration. So, and vibration is a necessary function because its probability is 100% during shipment. When we design the ribs and you have the loading necessary at the peak of the rib, you want to design the loading for a 25% deflection of the rib for the impacts. Now, I know that sounds a little gibberish, but let's look at it more carefully. Here's what we're saying. Here's the peak of the ribs. Depending on these, we have 3 different types shown here, but a pyramidal and a trapezoidal and a hemispherical rib. So the loading is simply the weight of the product divided by the area of the cushion. So the area of the cushion here is very small, which means that you're dividing a larger number, a weight by a smaller number, so you're going to have a larger loading. And this is exactly what you need for proper vibration attenuation. So design the vibration requirements, the loading requirements, using the peak of the rib. And then as the rib compresses, and what am I talking about there? Well, here we're talking about a 25% compression of this particular rib, depending on the shape of it. And you can see that as it compresses more, there's more and more area involved, and therefore the loading is going to go down. And as the loading goes down, we would expect that we could get to the point where we'd satisfy the shock values from the cushion curve. So that's how we do it. That's how we combine the design criteria for both vibration and impact when they don't coincide in terms of the same static stress loading. That's how we do it. Okay. Here's a graphical representation of how that same thing might work. So on this cushion curve, impact curve, we see that the proper loading might be between 0.37 and 0.70, in this particular case, grams per square centimeter. But then we see that for vibration, we need a loading of at least 68 or more grams per square centimeter in order to achieve loading that's inside of this attenuation zone, which is exactly where we want to be. So what we do then is to load at the peak of the rib for this value here. That's the vibration value that satisfies the peak of the rib. And then at 25% deflection, we will want to load the rib to achieve this, a value that forms within this range. So by so doing, we can keep to the criteria of the proper loading and still do both vibration and impact data properly. Okay. Some points to remember when we're going through this process, and I keep talking about this, but it's really important. Don't ignore vibration. It's 100% certain. So unless your client or your customer is next door, which isn't the case, or normally half a world away, vibration is going to be 100% certain because it happens from the vehicles in which the product is shipped. So when vibration and impact loadings don't coincide, don't just ignore the vibration. Okay. So also remember that the procedure used for running cushion curves may have a significant effect on the usefulness of that data. If you look in ASTM D1596, for example, the procedure for running cushion curves, it doesn't talk anything about using the data for design purposes. It just says, here's some method of evaluating its impact characteristics. And in fact, it's really designed to compare one material to another, not really for design purposes. So again, the use of ribs in the cushion design can have a very positive result, so don't ignore those results. Okay, here's some examples of ribs. These are more or less trapezoidal shaped ribs, and you can see they're very consistent with the design of the product and the package system. They work very well. And again, the vibration characteristics are determined by the peaks of the ribs. These are the points up there, because the deflection necessary for vibration is very, very small because the acceleration levels are very small. Okay. For impact, not the case. You've got all this material available for your impact characteristics. On the right, we see some ribs that I refer to as linear because they don't have any cutouts in them, so they're more or less uniform or linear in their deflection characteristics. But again, it's one way of reducing the amount of material and therefore increasing loading in order to get the PSI, the static stress that you really need for the design purpose. Okay. There's some other issues that are important when you fabricate a cushion system, not just its dynamic characteristics. One is sustainability, of course. We recommend that you don't glue the foam to the corrugated or anything like that, because you're going to reduce its ability to be recycled. The highest yield comes from good, smart design work, and it also will give you the lowest cost. Early in my career, I would design some killer packages, but they were so inefficient that no one bought them simply because I didn't look at the yield that I was getting from the material. It's normally supplied in a bun or in a plank format. So the more you can utilize that entire plank or the least material you throw away, the higher your yield and the lower your cost. And typically package suppliers have best ideas for this, so I would encourage you to use their capabilities. Another of the characteristics that I'm interested in you knowing of the issues is nesting. Cushions by their nature are very bulky, and therefore they're going to take up a lot of space, and space is money, especially during shipment. So if you can design a cushion system that nests before it's utilized, you're going to wind up with a much more efficient design, certainly in terms of cost. And then finally, corner protection. We talked a lot about flat impacts and things like that. Well, it turns out that, yeah, those are the most severe from a transmitted deceleration standpoint, but they don't happen very often. Corner and edge impacts happen all the time in the distribution environment, so they're very common. So make sure your package system is tested for those kind of impacts, and that your design is suitable for corner and edge impacts. Void corners are a big problem in package systems, so don't go into void corners. So finally, we're going to stop here now, and going to ask if there are any questions. Greg, is there any questions that we can address at this particular time?
Thanks, Herb. No, we don't have any questions at this point. So remember, everybody, you can send in the questions in the chat pane located near the bottom of your little control panel there. So please send them in if you get a chance. If you think of anything afterwards, we'll let you know where to send those to. Back to you, Herb.
All right, let's continue with the testing portion of the webinar. So we've got the package system designed as we like it. So when we are testing this final package system, there are some points to consider. Remember that it's not necessary to duplicate or to what's referred to as simulate the distribution environment in the laboratory during this test. You really know what the environment is. We've already discovered that. What you're really concerned about is how does the cushion respond to the product, and in particular, does the cushion offer the impact and vibration protection when the product is most sensitive? If the answer is yes, then you really don't care what the distribution environment is like, because the package system will protect the product regardless of what comes along. Remember that the product doesn't really know what's around it. It just knows vibration and impact sensitivity, really. So the criteria for vibration in the test is that the package resonance should be 1/2 of the lowest product resonance. I'll explain that more in a minute. And then when that happens, the cushion system will attenuate vibration at all product critical frequencies. Typical methods for checking this include things like random vibration, and oftentimes we'll use a flat spectrum as opposed to a shaped spectrum. A shaped spectrum is one that's designed to duplicate a particular type of vehicle. Oftentimes you'll actually see sine vibration used for this purpose as well. Remember this spring mass model from the earliest webinars? Well, we're doing it again. Here is the mass, and that's our product. Okay, it's sitting on top of this cushion system, which we're compressing, and therefore it becomes our spring. Okay, so we excite this system by exciting the base, and we measure the amount of vibration then transmitted to the product in this particular case. Very straightforward, actually. This is the typical plot that we get from a product resonance search test. We talked about this in webinar number 3. Okay, so this would be a typical product vibration transmissibility plot. We see that the product shows a natural or resonant frequency right here, about 29 Hertz. Okay, so that's our starting point. That's what we want to protect against. Okay, this shows a typical package vibration test result, and we see that the package resonance occurs here at about 12 Hertz, 12 to 13 Hertz, something like that. Okay, so that's the package system. So when we put them together, okay, here we show the package responding at about 12.7 Hertz and the product at about 29 Hertz, and we see that we have this separation range. There's a 1 octave between the package resonance and the lowest product natural frequency. Okay, so what happens here is that at the product natural frequency, 29 Hertz, you can see that the package system is attenuating. You can see that this line is below 1-to-1 over here, so it's transmitting less than half of the vibration input to the product at the product natural frequency. That's really what we're trying to do. That's the whole purpose of it. Okay, and that when we get this 1 octave separation between the package and the product, the lowest product resonance, then we have good attenuation for vibration. We also see that we have higher natural frequencies in the product. We have one here at about 100 hertz and another one here a little over 200. Okay, so we can see that the cushion system is attenuating those very well. It's got something going on here that we really don't know about, but it's as long as you have the lowest product resonant frequency covered by your cushion design, you're golden. That's really where you want to be. Okay, so that's the vibration impact requirements. Let's talk a little bit about shock, okay, or impact. Okay, so these impact tests should verify that the deceleration levels are below what we need, and we measure that by putting a accelerometer, typically, on a rigid portion of the product. Now, rigid portion of the product, that's not in the critical component, because we already know what that does. So what we want to find out is the input to the package system. We're not the package response. Okay. Typically, flat drops are used for this because the highest deceleration level occurs when we dissipate all the energy in one axis, which is what happens with a flat impact. Corner and edge impacts are conducted to verify the integrity of the package system, and as I mentioned earlier, they're the most likely to occur in distribution anyway. Okay, so make sure you do corner and edge impacts. Okay. As a practical matter, the ISTA, International Safe Transit Association, has a procedure that they call the 10 drop sequence, and it's become kind of the de facto standard for package impact verification. And it requires 1 impact on each of the flat surfaces of the package, and then 1 impact on a corner, and they specify the most vulnerable corner, whatever that happens to be, but generally speaking, it's the base corner where the manufacturer's joint is located, and then 1 on all the edges that radiate from that particular corner. So here's a list of them. So the most fragile, face, the 3-corner edge, and the shortest edge, the next longest edge, and basically what they're doing is saying you just drop on all these edges, and then 1 on each of the faces, starting with the smaller face and leading to the largest face. So that's the ISTA 10 drop procedure, and it's very common, often used. Testing is normally done on a drop tester because we want to guarantee a flat impact, which these machines are designed to do, and we want a rigid impact surface, and again, these machines are designed for that. So it's important that the machine be guaranteed to deliver this flat impact all the time. That's why we use them. As noted earlier, accelerometers are put on the product in order to show the deceleration levels transmitted through the cushion. So in this particular case, we have an impact with the X, Y, and Z axes all monitored, and we see all the energy is transmitted here in the Y axis, and it has a level of about 57 Gs or so. So that's the transmitted deceleration, and that should be below the product fragility in all axes. So you want this number to be below that critical acceleration. If you have an example like Edmund used, where you're using about 70 Gs as the magic number, this would be a passing score. This will also give you the velocity change that is produced. In other words, that's the area under this particular plot. It's a measure of the momentum dissipated during this event, and it has to be within the range of the drop height plus the coefficient of restitution. We'll talk a little bit about that later. But this is a typical piece of data from a drop test that will tell you whether or not you've done the job correctly. Okay. There are some variations of this waveform that are important, and we're going to talk briefly about those here now. For example, over here, when this deceleration waveform is symmetrical, in other words, this rise time from here to the peak, okay, it's approximately equal to the decay time from the peak down to the 0 point, then you know that your cushion system is properly loaded. Okay, when this rise time again, from the 0 point up to the peak is very short relative to the decay time, then you know the cushion is underloaded. In other words, it's too stiff. You don't have enough load to compress the cushion, or there's too much cushion. So it's just too stiff. So that's a key to note there. So when you have a rise time that's very short relative to the decay time, you're underloaded. And then the other extreme is when your rise time is very long relative to the decay time. So in other words, it takes this thing a long time to bottom out, which it eventually does. Oftentimes you'll see a higher peak acceleration here too. Then you know your cushion system in this particular case is overloaded. You have too much weight or too little cushion. So those are three of the what we call waveform morphology issues that you can identify very easily from your package impact performance test. Okay.
Thank you, Herb. So right here we have theoretical test results as if you were actually doing the drop test per ISTA 2A. So if you remember our previous product of the laser attached to the robot, we know that the maximum deceleration that we want to see on the unit during testing is 70 Gs. And then so, you're going through this drop test, so you're doing the corners, you're doing the edges, you're doing the sides, and pretty much what you're doing is that you're just checking your numbers. So you do a drop and you make sure, okay, everything's good, everything's less than 70 Gs. A drop to a drop, everything's less than 70 Gs. But then, in this case that we have here, we have one value that is actually over 70 Gs, which is 75 Gs, which is right here. And then so theoretically we're going to fail this unit just because it exceeded its maximum G levels. And what that means is that since we did the damage boundary testing and we know that it actually fails at 70 Gs, 75 Gs should theoretically break the unit. So that's a test result there that we actually have a failure. Next test input, or the next hazard that we talk about, is vibration. So same deal, we're testing per ISTA 2A, and when you test per ISTA 2A, what you do is that you vibrate it on the base down, top down, side down, and end down. And right here, once again, we're just checking numbers again, We're making sure that we have attenuation before or at 70 Hertz. So these values, they check out perfectly fine. We have attenuation at 50 Hertz, 60 Hertz, 45 Hertz, and another 50 Hertz. So everything's under 70 Hertz. And we're good to go, and we could say that. So at the end of the day, you ask yourself, okay, was that 75 Gs? Was that enough to actually fail this package? We're actually going to talk about it a little more. And with that, we have decisions. So if your engineering package passes or barely passes, which our example had 70 Gs, 75 Gs, very, very close, it's designated package performance test, you have a couple decisions. You can theoretically ship your package through its distribution environment with little worry of product damage, or you can perform margin testing to determine how much packaging waste is present in your package. So these two are very, very two different cases. One, you're just shipping as is. You assume that your package that you have is going to be the final product. And the second is that you're trying to optimize your package to eliminate all the waste possible. Both has pros and cons, and we're going to talk about both cases right now. So when you're shipping as is, like, your test pass or marginally pass, and you make the decision, okay, we're just going to ship because, well, probably these three reasons. Number one, you're probably under a time constraint, which means that your builds are ramping up, units aren't being made, and your units have a deadline, which is probably pretty close. And making an optimal pack is probably just not feasible within the time constraint. And if you do rush it, you might end up with more damage than anticipated, so you definitely don't want that. So that's the first reason why you should just ship as is, and you probably don't optimize your package, or you might optimize your package later on. But right now, you have deadlines to meet. Second item is that, okay, maybe we're just going to ship as is because we have a relatively high dollar product. And what that means is that it's acceptable to have additional protection and, kind of quote-unquote packaging waste because a couple of reasons. High dollar product, and maybe because you don't sell that many of these types of products to begin with. If you ship out 100 a year, but each product is $2 million, it's perfectly fine to have packaging waste because there's very, very little of it. But if your product is a $50 toaster and you ship 10 million a year, then packaging waste is probably a lot more, it impacts your bottom line a lot more than the previous example. And the third reason why you probably want to ship as is, and that's probably like the example that we had previously, is that we had borderline or barely acceptable test results. And if that's the case, you probably can't reduce the packaging to begin with. So you know what, we're just going to ship right now and use this as our final packaging. But if you do have time and resources for margin testing, these are the reasons why you should actually do it. One is that the results are significantly better than anticipated, which means that, okay, we wanted 70 Gs and 70 Hertz. And for some reason, you saw 40 Gs and 50 Gs, nothing even the 60 G range. And that means that, hey, we have a lot of wiggle room here, which means that we could probably cut down our package by, maybe a couple inches, half an inch or so, but that's all theory craft right now. But you know that your results are significantly better, so therefore we definitely have packaging waste. And second is that you just want to reduce overall costs. We have material costs, which is, cost money, but more importantly, we have supply chain costs. And we're going to talk more about that in the couple of slides as well. So one thing I want to just hammer through today is that transportation cost is always the most expensive logistical expense in the supply chain. Transportation, whether you do your research online, research on a book or something, it's always going to range. It's always going to be the most expensive cost, but it's usually around, I would say, 40 to 50%. And here's an example that I pulled from a book. The book is called Supply Chain Strategies by Fragility, but then there's just a straight photocopy, and it shows that transportation cost is 44%. And that's huge, 44%. So anything that you could reduce of that 44% will definitely help your company and help the bottom line of your product. And there's just another fact that I pulled online as well. So that's from the source on bottom, prioritylogistics.net. But then that is a whopping 58% of freight transportation costs. So we had one example of 44%, 58%. But like I said, I just wanted to hammer in that transportation cost is really, really expensive. So anything that you could do to reduce this cost would be highly, highly advantageous to your company. So you want to ask yourself, okay, how do you actually reduce your transportation costs? Well, the way that you do that is that you reduce your overall cube by reducing your package size. And what that means is that once you reduce your cube, you can fit more units on a pallet. But then it doesn't end there, because pallets usually go in an ocean-going container. And then so that means that you can fit more units on the ocean container. But the final result is that you just drastically decrease your transportation cost. How do you accomplish this? Well, you could grind out the numbers in Excel, but that's usually very, very grindy and very, very, very time consuming. And your results will probably not be as accurate as if you just use specialized palletization softwares. So here's two examples of this software, and one is TOPS, which is Total Optimization Packaging Software, and another one is just a K-Pack software. So on bottom, we just have an example of different types of pallets and a layout that it would give you. But then pretty much these programs, they auto-palletize and containerizes your packages based on specified dimensions. So the interface of these programs, they look something like this. So on the left-hand side, we have what is known as just shipper parameters. So they have a lot of nitty-gritty details that we're not going to go through every one today, but then you can see that you could definitely define the length, width, and height of your package. You also will specify other types of values, such as whether you want overhang or not, and the pallet size. But then all that is pretty customizable. So when you're trying to optimize your cube, what's happening is that, okay, you're putting in the number and say, okay, if our package is 10 by 10 by 10, how many can you fit per pallet? And they say, okay, what if you have a 9.5 by 9.5, 9.5? How many can you fit per pallet? And it's actually pretty empirical that you're just grinding numbers, but then you see that, okay, this reduction gives you this many units, this reduction gives you this many units. And it's kind of repetitive, but then at the end of the day, you know exactly the breakpoints that you need to actually get how many units on a pallet. And that very, very little reduction can save a company a lot of money. And we have some examples of that in the future slides as well. So here's just the interface of these programs here, and the package size and pallet size. And like I said, once again, automated results. So here's a different package we have here, but then specify the package size, and it says, okay, based on that, we could fit this many units per pallet. And then also based on that, we could fit this many units on an ocean-going container. And with that, you have some values of efficiency. So we have right here area efficiency and cubic efficiency. So with this design here, you could fit, it says you're around 84% cubic efficiency. And also, it also shows that the units per vehicle is going to be 2,400 right there. So, that's just the numbers that it just spits out for you. But again, these automated programs are definitely, I would say, the key to cube utilization.
Hang on just a second, folks. We're having a microphone issue here with Mr. Edmund, so he'll be back here in just a sec. Okay, Edmund, take it away. Nope, nothing yet. So just by a raise of hands, if you could raise your hand and let me know if you've been to all 5 of these sessions, that'd be great. So if we get a raise of hands of everybody so we can see who's been here. So can you guys hear me okay? Okay, so Edmund, back to you.
Okay, so right here we have a case study that I fabricated just so the audience can better understand just the importance of cube utilization and how much efficiency you can increase and how much you could actually save a company theoretically. So right here on our first design, we have a toaster that you could fit approximately or exactly 60 per pallet. And this package dimension is 16.43 by 9.35 by 9.35. And again, this is the original configuration. So there's theoretically no reduction in size, which means that we're not reducing the package, and there's no increase in efficiency. And just for ease of calculation, we're going to assume that we ship around $1 million worth of annual freight based on this design. So the proposed design, which is the next design down, we actually could fit 90 per pallet. But how do you get 90 per pallet? You get 90 per pallet by reducing your package by 1 inch on each side, which means that because foam end caps are usually left to right, bottom, top, and front back, it's half an inch on each of the 6 faces, and that will result in a 1 inch reduction on each side. And if that's the case, the calculated increase in efficiency is 150%. But more importantly, the cost reduction is 33%, or will cost the company $666,000 instead of $1 million. And lastly, we have the third or the second proposed design, and that's a reduction of 2.5 inches total, so 1.25 inches on each side. And that will give you an increase of efficiency of 245%, and it will allow you to fit 147 units per pallet, and a 59% reduction in cost as well. So let's see what these designs look like when you actually put them into the automated programs. So this is the current design once again, and the current dimensions, and you could fit 60 per pallet. And again, no increase in efficiency, and theoretically this is going to be $1 million annually. Second design, first proposed redesign, is that you take off an inch on each side, and if that's the case, you increase efficiency by 150%, and you have a 33% reduction in cost. And this one you could fit 90 per pallet, and then on bottom you could see that that's the design, and that's the pack out or palletization pattern. The last redesign, you actually fit 147 units per pallet, and you take off 2.5 inches on each side, and that increase in efficiency is huge, 245%, and gives you a 459% reduction in cost. So this is the final slide of our webinar, and also the final slide of the cube utilization. And so a lot of people might be asking ourselves right now, okay, how do you actually reduce your cushion or yeah, like what justification do you have? And there's different ways that you could do that, but one way that we could do that is just simply, for instance, if you have conservative pack, when your test results are significantly better than your fragility of your product, and you say, hey, I am using way too much package here. Second way that you could actually do this is that you could improve the product robustness, increase the fragility of it. And if that's the case, you have a quote-unquote borderline package, but then you increase your product fragility by 20 Gs or so, and that'll let you chop off at ½ inch on each side, theoretically. And then so that's another way that you could improve your cube. And it's a pretty big topic, so we're not going to delve too much about it this time, but maybe next time in our future webinar. But that ends our webinar. And we have some questions from the audience. I'll actually answer the first one. And the first question is, what is 1 octave separation between product and package? So when you talk about the 1 octave separation, you're mainly dealing with waves and resonances. So whenever you deal with a resonance, for instance, let's just say it's at 50 hertz, your resonance. So 1 octave below would be exactly half of that, which would be 25 hertz. 1 octave above would be double that, which is 100 hertz. How does this apply to package vibration and what you're designing? So what happens is that whenever you have a frequency, when you go 1 octave above, it actually goes, so let me just re-explain that. So if it amplifies at a certain frequency, when you go 1 octave above that frequency, it is guaranteed to attenuate at that certain frequency. Let me give you an example. So you have a product resonance at 50 hertz. And then so what you know about product resonance is that you want your package system to be at attenuation at 50 hertz so you can mitigate those amplifications. So you want your package system to amplify at 25 hertz. So at 50 hertz, you're attenuating 50 hertz. And that's the idea of the 1 octave above or below, depending on your applications. And Herb has some other questions that he wants to answer, so I'll hand it off to him.
Okay, thanks, Edmund. I'm sorry that we didn't explain the term octave earlier. Those of you who play a musical instrument certainly know what an octave is. I could sing it, but I don't feel real well now, so I won't bother you with that. But as Edmund said, it's a doubling of the frequency. Okay, so I hope that was clear. If it's not, we'll try to explain it later. We had a question about rib shapes, and in particular, should a rib shape be linear or should it be non-linear, things like that. Good, and that was an excellent question. It's best, from my experience, to play around with linear ribs. What do I mean by that? Well, ones that when they compress don't change shape. Whenever you have a rib that changes shape as it compresses, in other words, it's one of those trapezoidal or pyramid-shaped ribs, then you're into what's referred to as a non-linear design. And as Edmund mentioned earlier, it's probably a little bit outside of the complexity necessary for this very basic series of webinars. But you asked the right question, because we're going to cover that in our next webinar, The Tricks of the Trade, next month, and you'll be getting a notice about that. But in general, for non-linear cushion designs, we're very interested in making sure that we don't violate some other rules, such as column buckling of cushion materials and static creep, both of which are important. And we did not mention those earlier, but they are important. So don't think that the rib shapes that I gave you are the right ones or the common ones. They are simply ones that I used as an example to explain the concept of a variable loading on a cushion in order to satisfy both vibration and impact. Okay, so I hope that's clear now. Another question that was asked earlier was, we've seen cushion curves, but not the vibration data. Are those hard to get? And the answer is, unfortunately, yes. And they're hard to get because, quite honestly, we don't demand them. Where do they come from? They come from the material suppliers, and they should tell you this. I mean, they should actually give this data to you, but most people don't demand it, so they don't care about it, and therefore it kind of falls into no man's land, if you will. So demand vibration data from your cushion supplier if you need that. Okay. Another question that occurred earlier was void corners. In other words, if you design a package system and you use good layout techniques or good efficiency, as I was mentioning earlier, oftentimes you wind up with a design that works well in the flat drops, but the corners or edges of the cushion system on the package are void. And that's something you should really be careful about, because even though you're only going to be testing one or two corner or edges during your package test, the distribution environment tests all corners and all edges, guaranteed. If you think about it, a flat drop is pretty hard to do. We have special machines designed for that. But in the distribution environment, the UPS gorilla, I'll use that term in kind of tongue-in-cheek, it would be pretty difficult for that person to do a flat drop all the time. Packages just gets tossed. That's what happens. And when they get tossed, they land on corners and edges most of the time. So they're very frequent. Now, are they damaging in that area? They certainly can be. So don't ignore the corners or edges. In other words, void corners or void edges in a package system are probably not a good thing at all. Okay. There's a whole bunch of other really good questions, but we're up against a hard timeline here, so I'll be answering, and both myself and Edmund will be answering these to the people who asked them online, and we'll incorporate these into the other webinars as well. So you'll have a chance to see them again. But really, really, really appreciate you folks submitting questions, because they really help us in tailoring these webinars in the future. So Greg, back to you.
Thanks, Herb and Edmund, for that great presentation and getting through as many questions as we could. And thanks for everybody who sent in the great questions, like Herb said. We appreciate it. And if you think of anything afterwards, please feel free to send it in to either Herb or Edmund. Herb here wants to say a little bit more about the upcoming webinars. So Herb, back to you.
Thanks, Greg. Well, we've done a most ambitious project here. This is what we told you that we were going to do in January, and now it's in September, and we've actually done it. We've taken you all the way through the webinar series on protective packaging dynamics. So we taught you all that you see here, and it's been an ambitious ride. We thank you for joining us. I hope it's been effective for you. And again, the value of this whole thing is that you now have this online. You can go back and look at it whenever you want. And gosh, look at the bright side. There's no final exam. So you have all the information necessary to design and test a protective package system. We do know that there are some shortcuts. There are some things that you should know about in the meantime. And some of you have asked us about those in the course of these previous 4 webinars. And so what we decided to do was to kind of put those all in a bushel basket and show you exactly what they look like. So in next month, we'll actually have a webinar that will look at kind of tricks of the trade, as I call them, some key elements, some typical design features, some easy to do things to save a lot of money, things like that in the process. So you have the basics in the in these 5 webinars, and we'll actually have the kind of the frosting on the cake, if you will, during the next webinar. And I wanted to thank all of you for joining us. I wanted to make sure that that you benefited from the whole thing, and I really would like your feedback. All of us would, in terms of what you liked and didn't like about the process. So please return those forms that will be emailed to you, because they really help us a lot. And again, thank you so much for your attendance and your participation. Greg, back to you.
Thanks, Herb. Remember, Westpak has 2 locations, one in San Jose and one in San Diego. Please feel free to contact excuse me, either location. If you missed anything or would like to listen to the webinar again, please go to Westpak's website at www.westpak.com under the Resources Webinar tab. The webinar material should be uploaded by Monday. We'll be sending out, as Herb said, a short survey. Please fill it out as we are always trying to improve the process and see what you guys think about the webinars. And if you have any other new topics or ideas, please list them there. If you think of any other questions you have during the webinar or come up with afterwards, please feel free to put them there or send us an email. If you have anything else, like I said, please send it in on that forum or email us. Thanks for attending today's webinar. I'm Greg Swinghammer. Make it a great day.